Is it okay, everybody?
It's okay. Perfect.
Okay, good. Okay, so let's start. I don't know if people will come a little bit later. Okay, we'll miss the beginning. So, okay, sorry I didn't change the title, but anyway, I'm going to talk mainly about the growth of lithium niobate thin films. This is a topic which I'm working many years today already, since 2010, more or less, let's say. And the applications which we mainly considered, it was high frequency acoustic devices. Okay. I come from a university which has changed name recently, so Marie-Louis Pasteur, just called it was previously it was Université Franche-Comté, so it's regional university. But also, and I do research at Institut FEM2ST in Besançon, and at the same time, I'm also attached half-time in CIDUZEN in Paris in Palaiseau, with University Paris-Saclay and CNRS. And also I belong now also to Institut Universitaire de France. So a lot of affiliations at the moment. Okay, so let's start to talk about thin films of lithium niobate. So, I mean, lithium niobate is very mature material in the form of a single crystals. It's used in photonics, it's used in acoustic filters, produced in industrial scale with 6-inch or 8-inch size diameter wafers, cheap wafers. So it's very robust material, very well-known material. And basically, when the people started to work on the single crystals, we understood that we will need this material in the form of a thin films. And then there are a lot of groups in the world who worked previously on the growth of lithium niobate. And because this material is needed for miniaturization, integration, or better performances in the form of thin films. And then about 2010, most of the groups in the world stopped working on the thin films, on the growth of the thin films, considering that it's too difficult. It's too difficult, and at the same time came also bonding techniques, polishing, trimming, and ion slicing, and so on. And the people completed this need by making single crystal films. So basically what I will call here top-down technologies. Okay, so basically we produce high quality single crystalline films by simply bonding and grinding and polishing down. And that is very good method to obtain, for example, 10 micron thick lithium niobate, 3 micron, 5 micron, a micron thick films, and bonded on any substrate. Right? It can be bonded on any substrate. We can obtain any orientation by simply bonding and polishing. What this becomes a little bit more complicated when we need to go down to the thickness below 1 micron. It's still possible because we have the trimming techniques, but it's difficult to control the thickness precisely. And another thing, we use all the complete wafer to make one single film. So it's like limitations, but the main limitation, I would say, the thickness control, but it's very good methods for making thick films because we get a single crystal quality films. And of course, even for thin films, you can do a work, but then you need to do a lot of trimming and so on to catch the homogeneity of the thickness and so on. And then in parallel, we have ion slicing. So where you do implantation. Then if you could cut your microphones, it would be nice. Okay, so then ion slicing, when you do implantation, then you do bonding, and then cleavage by heating, and then you have also annealing to recover the properties because implantation damage the crystal, and then polishing to get back the quality of the surface. So basically, in this case, you could reuse the initial wafer several times to get the wafer, but we have a lot of steps to produce a film. The film thickness, it will go from, let's say, 250 to 1 micron, maybe 900 nanometers. It will be limited by implantation depth. So we cannot make thick films by this method. So the film is still single crystalline quality, but it slightly has a damage effect. Okay, it's not that quality when we have polishing. Polishing doesn't damage at all the crystal structure. Implantation will still have some effect on the structure. So it's not anymore this perfect single crystal as before. Of course, we did annealing and so on. So it's mainly the properties are recovered. It's very high quality film, but it's not exactly the same quality as it would be when you just do polishing. Okay. So when we say single crystal saw some damage implantation. So there is some effect behind. And then, of course, the thickness variation will be about 3% plus minus 3% across the wafer. So the size of the films, of course, it will be limited in these top-down techniques by available wafers, right? So 6 or 8 inch. Then it's always done from congruent lithium niobate crystals. And there are several companies who are selling these ion sliced films or doing or polished films. Okay, in United States, in China, in Europe, in Japan, and the films which are bonded and polished, it's already in acoustic filters. I'll show a little bit later. I don't know if there is a industrial products based on ion sliced films. The films are sold at industrial scale, but I don't know if there is already products like filters or other was already produced on industrial scale. I don't have this knowledge. And then the last method, which was abandoned, and of course it was very difficult to continue to make a competition with these single crystal films by the growth. So that's why when these films came, then everybody just sort of abandoned the growth. Because when you grow the film, of course, it depends on the substrate. It's very difficult to get single crystal quality film. The substrate, you are limited on what you are growing because you need epitaxy, so your substrate orientation. Then you can use sapphire, mainly sapphire substrates have been used. So we have a lot of limitations. And of course, when you do heteroepitaxy, your substrate has different thermal expansion. And then you get the limitation of the thickness because the film may be twinned or cracked and so on. So basically, if you do homoepitaxy, then your thickness is not limited, but then you have less of interest of doing it. And then epitaxy stays a little bit on the side of all these methods and is considered as less mature, let's say. And me personally, I started to work on thin films when everybody abandoned. So it was very amazing time, let's say, when everybody don't believe anymore that you can do a films by the growth, and you're trying to convince that probably still possible. And then, of course, now we came also to another strategy because now the bonding, heterogeneous integration, we're doing in all different topics. So the same for the thin films, I'll show at the end of my presentation, we go to the layer transfer techniques because now it's in all the developments, we will find this bonding transfer and so on. So if you ask me today which technique is the best, I would not say this or this. It depends on application. It depends on the price which you can afford to yourself. And we are not really in competition. I would say probably we need all of them three of this type of techniques for fabrication. So my presentation will be mainly on epitaxy, on which I'm working since 10 years. And let's look why it was difficult to grow the films and what is where we had to work on. So the first thing when we start to work with lithium niobate is to know that lithium niobate, it's a material which has a broad non-stoichiometry range. So it means that lithium niobate phase, very frequently we will write lithium niobium-O3 in all the papers, but it's not true. It is the formula is 1 minus X and so on. And normally the concentration of lithium is 48.3 mole % in the congruent crystals, in the crystals which we are buying, on the films which you are buying. And sometimes in the smart cut films, the lithium concentration is even a little bit lower than that was in the congruent crystal. It depends on the process which was done. And if a film lost lithium during diffusion, for example, to the silicon dioxide, and so on. So this phase exists in very broad range, so from 46.5 mole % to 50 mole %, and the properties of lithium niobate are highly dependent on lithium composition. So if we take some examples, which might be interesting, let's say for HINA project, so like coercive field, it changes like by several times. If you change your concentration from congruent composition to nearly stoichiometric one, so you change about 1.5 more percent, then we see that refraction index or birefringence is changing, electromechanical coupling changes, so velocity is changing, so acoustic velocity is changing. So basically, if we want to bring this material to acoustic application, to acoustic filter application, where your frequency has to be precisely controlled, we need a precision in composition of 0.2 more percent in lithium to be reproducible, and we need control in this level. I saw for the single crystals of lithium niobate in photonic applications, we require precision 0.1 more percent. So it means we need to be very precise. And then what was done mostly in literature before, when the people grow thin films, they do X-ray diffraction. They do X-ray diffraction to check if the film is single phase, if the phase is pure. But basically, if I do X-ray diffraction even on the powders, I would be able to say that, okay, my phase is pure in this range. So it's even not, I cannot confirm that my film is exactly here. And there are also some orientations which, for example, your parasitical phase has exactly the same position for your exactly the same position of X-ray diffraction and reflection as your lithium niobate. So this is, for example, orientation Y-cut. You almost never see the parasitic phases, even there is full of them, because your X-ray diffraction pictures superposing to each other. So X-ray diffraction was not adapted method, and another thing, that lithium is very light element, and you cannot measure them directly, the composition, by direct methods, especially with such precision. And even when you buy a single crystal, the composition is never indicated in more percents. In most cases, for example, if you buy lithium tantalate, they will say Curie temperature is 603 degrees of Celsius, or for stoichiometric crystal, it will be 690 or 700. So basically, we give the physical properties to indicate what is the composition of a crystal. And even the single crystals, when we characterize the composition, we use indirect methods. So it means that we measure the properties, and then we estimate how much we have of lithium. So we do calibrations as a function of stoichiometry, and then we use these calibrations. So in our group, I started to work, my career started, I worked on non-stoichiometry in lithium tantalate single crystals before starting to work on the thin film. So I have a long experience on lithium non-stoichiometry in these materials. And we use Raman spectroscopy. Well, it's a method which we have. I'm not saying it's the best method. There are a lot of methods how you can estimate lithium composition. But just we get used to use Raman spectroscopy. It's very precise. You can do a mapping of the concentration. And then we have here an example how it is in lithium tantalate, how much is changing the width of the Raman modes, which are sensitive to the number of defects. So we can get very precisely a composition if we have a calibration. So in single crystals, we can measure the composition of lithium with a precision of where's my mouse, of 0.05 more percent. Well, when we go to the thin films, of course, we can use the same approach or similar calibration, but the problem is that the films contain other effects, like, for example, residual stresses or other defects. If your film is textured or contains a growth domains, it means we have a grain boundaries, and when grain boundaries induce the defect, and all this will make additional broadening of a mode. Okay, so in thin films is more tricky. You have to, for example, if you ask me to say how much you have a lithium in polycrystalline film, I will not be able to tell at all how much it contains of lithium. Okay, so in very high quality films, I could go probably to 0.102 more percent precision. But then in relative scale, it's much easier, let's say, to compare. So it depends. So it depends a lot, and not always we can have this precision. But in very high quality films, where you single crystalline quality films, then you probably can say more or less, at least you can say that your composition, you have more lithium than this. This is how you can estimate lithium composition. And another problem is that lithium oxide is highly volatile. And then we do the growth of the films under vacuum conditions and at high temperature. And then it means that from film, the lithium oxide goes out very easily. And when you grow the films with volatile components, so it means that, for example, your composition will be dependent on the thickness of the film, your composition will be dependent on the growth orientation, on the substrate conductivity, substrate thickness, polishing, backside polishing quality, and so on. So it means that you need to optimize composition for each thickness, for each substrate, and each orientation. And that it becomes complicated if you use the physical methods, because then you need to change. I'm not saying that it's not possible. I'm just saying that it's difficult. It means that you need to change the target each time. Of course, you can tune a little bit the conditions to play on, but it's not that straightforward. And when you use the plasma containing methods, lithium is a light element and just going to the side of the plasma. But for example, if you do a sputtering, then you will find that you have not enough of lithium in the middle of your wafer, and then too much of lithium on the side of the wafer. And then, of course, you can find a place for research purposes somewhere in between where the lithium composition is correct. Yeah, so it's possible, but it's quite complicated, and that's why we selected. I had the opportunity to do also a sputtering of lithium niobate, but I prefer finally to work on CVD techniques, which allows you to tune the composition easily from one deposition to another one, and to adjust very finely. So at FEM2ST, we worked together in collaboration with Anilsys, who gave us DLE CVD machine for 4-inch wafers. And so we have two injection heads on which so we can use in one. So we use the solutions of metal organic precursors. So I put lithium THD and niobium THD4. Up. And basically, we use these two injectors, so we can place one solution in one canister, and the second, and to adjust very finely, because how much we inject of each of these solutions, and we can change easily from one deposition to the second by changing just injection rates, and the injectors we are controlled by computer. So as it's a CVD method, we have very nice thickness homogeneity. And also we showed that we can control the lithium composition. So we can tune by changing just the ratio of the two precursors, but also, for example, by changing the pressure or other conditions. So we can tune very, very finely. And also we can do the films which are nearly stoichiometric. So as you can see here in the Raman mode of a film, which in red, they are thinner than the modes of a single crystal of the same orientation, which indicates that the film contains less defects than the congruent crystals. And we also measured a composition homogeneity across the wafer, which was already the rare groups who measured lithium composition inside of the films. And additionally, almost nobody showed homogeneity on the big surfaces. So here you see, we measured by Raman on different points. We had much more points. I just put it like 4 to show what we are in the errors. Basically, my precision. So I put absolute precision for single crystals. Okay, so we saw that it's varying from absolute value very, very, very little amount. And basically, it's in the errors. So it shows that the composition across the wafer is homogeneous. So let's move now to the application. So if we take now, for example, mainly I work for acoustic devices. Well, we never went to the filters. We did the resonators, but resonators, acoustic resonators I use for acoustic filters. So we have two types of acoustic devices used, mainly, let's say, bulk acoustic waves and surface acoustic waves. So at lower frequencies, we have we use the surface acoustic waves, which is very simple, let's say, technology. Initially, it was just you take a bulk lithium tantalate or lithium niobate single crystal, and you do interdigital electrodes on the top, and then silicon dioxide for temperature compensation. And this allowed it to go like to 5 gigahertz frequencies with technology. And then very recently, Murata, well, recently 2016, released incredibly high performance SAW filters in which they used these 2-micron lithium tantalate polished films on which were bonded on a Bragg mirror, which allowed it to confine the energy and to increase the quality factor and also electromechanical coupling. And then we are able to get to much higher frequency, up to 3.7 gigahertz. So how we could go, so far surface acoustic wave devices at industrial scale were limited to these frequencies. And if you would like to go further, basically the frequency is limited by interdigital electrode wavelength or period, which is limited by stepper technology. So basically the wavelength in industrial process is limited to 0.8 micron. And then if we use single crystal, then the velocity will be limited by material velocity, which we cannot change in a single crystal. But we could increase the velocity if we put a film of lithium niobate on high velocity acoustic substrate. So for example, sapphire, silicon carbide is highly considered now, diamond, which would accelerate a lot of wavelength. So it means that we need the thin layers to accelerate and to increase the velocity. So this was new already also in 90s, or was simulated and known that we can increase the velocity, but when we needed to do very thin films to accelerate that. And we need a high quality film. So when you do surface acoustic wave devices, you need a single crystalline quality. So on sapphire, we know to grow a lot of different orientations today. I will not go to the details. Well, probably in one of the schools, we can go, of HINA schools, we can go to the details and I can explain you how it works, epitaxy, and how we can control the orientations. And I'm going to give a lecture in one of the conferences in Mexico in EFTF, and tutorial, and I know the tutorial will be available online when I'm going to talk about epitaxy of lithium niobate. So we can grow different orientations, Z, X, Y, 33 degrees, Y, 128. Now, I name all these orientations in acoustic, in IEEE notation. Of course, there is a crystallographic planes behind of each of this orientation. But single crystalline quality, we're able to grow only Z, Y, 128, 52 Y orientation as well on sapphire. So for example, if you look at Y-axis oriented lithium niobate, so it's very asymmetric. If you go look to the dance planes, this is here we have stereographic projection. So we have 0, 1, 2 planes, which are you see very asymmetric, and you see that we get those three planes as expected. So it means that we don't have any growth domain. We have single in plane orientation. So the same here, another example of Y128 orientation as expected. So this was 104 planes with smaller one dots. So we have 4 and 4 as expected. So nice rocking curve. Of course, I saw one paper who compared saying, oh, we have a rocking curve of 0.04 and others we had 0.25. Be careful about the precision or resolution of your diffractometer. So look to the substrate rocking curve. Okay, so in our case, the rocking curve of the substrate is 0.21, so it means this is the resolution of the diffractometer. So we need to compare comparable things and not just saying, oh, my rocking curve is this, and another one had like 10 times bigger because the resolution of the diffractometer was worse. Okay, so, and the films which have been studied a lot is C-axis oriented films or Z-axis oriented films. So we can grow such films on sapphire, on C-axis oriented sapphire, because sapphire is also trigonal structure, like lithium niobate, so it fits quite well. So we have a quite a mismatch between the structures, but we can still grow nicely epitaxial films. But when the films grow on sea sapphire, we have very frequently 60 degrees rotated domains. So if you look these three like dance planes, it will be rotated by 60 degrees. In other words, it would exchange x plus and x minus axis. So you rotate in plane just by 60 degrees. And when the rocking Bow figures in the structure would have 6 peaks. But we optimized the growth directly to get just one single orientation with nice rocking curve. We used these films as well to study vibrio spectroscopy to check our elastic properties if they fit. So we did the simulations of the frequency as a function of the wave vector of acoustic velocity. So and we see that basically our measurements, experimental measurements, fits very well on this theoretical data, which was just a single crystal data on sapphire. And when we did also surface acoustic wave devices, so resonators with a wavelength of 1 micron, and we got nice wave acceleration. The acceleration of the wave was shown already in early 90s, in 2000. But the quality the frequencies were much, much lower at that time because probably we didn't have e-beam technologies as we have now. But the signal was quite low at that time and noisy. Sometimes it was even difficult to find out the signal inside. And we had very nice signal at 5.5 gigahertz. And the wave was nicely accelerated and the coupling was as expected theoretically for this particular device. Well, but when to bring this to the filters, it would be difficult because dicing of sapphire is difficult. And when you have a single crystalline films on silicon dioxide and so on, and then high frequencies normally, I mean, even if you compare surface acoustic waves and bulk acoustic waves, surface acoustic waves, because of these tiny electrodes, we are not withstanding very well the high power densities at high frequencies. So surface acoustic waves probably will stay limited to the lower frequencies. But anyway, this is the state-of-art result on the grown films. Then, of course, if you would like to go, we had like 150 nanometer thick film, right? But if you want to go to the thick films on sapphire, then we get a problem of thermal expansion and thermal stresses. And then you get this nice twinning and cracking sometimes of the films when you reach about, let's say, 300 nanometers. And then it becomes a real limitation because if you do optical devices, when you have a scattering on these twins or cracks, and in acoustics, it's the same thing. So it's difficult to grow directly on sapphire thick films because of this relaxation of the stresses, because the stresses are high, because the thermal expansion in X or Y axis, it's like 3 times higher than that of sapphire. So the thermal stresses are very important. And then we started to work more on bulk acoustic wave devices. And basically we have, initially it was used aluminum nitride. I didn't put any image how it looks like. It was not very pedagogic to do that. So basically we have a membrane between electrodes, what we call TF bar, or we put a piezoelectric film between a sandwich of electrodes on a Bragg mirror. And these devices was done mainly on aluminum nitride, but to increase, and it was limited to 4-point-something gigahertz, 4.5, I think, gigahertz. And it was limited the films because it's very easy to increase the frequency in a bulk acoustic wave devices. You just reduce, because the frequency is proportional 1/over the thickness. So just you reduce the thickness and you can go up the frequency. But when you start to decrease your film to very thin film, when your electrodes, you cannot reduce in the thickness because you still need a good conductivity to keep a high quality factor of your resonator. And the mass of electrodes becomes very important with respect to that of a piezoelectric film. And that kills electromechanical coupling of device. So it was a limitation for aluminum nitride when we found in 2009 that it's possible to dope with scandium, and then doping with scandium helped to increase electromechanical coupling of these films, which is done just by sputtering. And now, basically, we can go to 6 or 7 gigahertz. Qualcomm announced 7 gigahertz on aluminum scandium nitride films in the both devices. So it's just textured films grown by sputtering. And when other techniques came, like, so for example, with lithium niobate ion slice films, which are very thin, so it can go to 250, 300 nanometer thick. And then it can be integrated in the same both devices. So I will show some examples after. And then there's also X bars. So it's like more lateral excitation came. So it could go probably to 8 gigahertz, something like this, because the lithium niobate is like 3 times more coupled than aluminum nitride. So it helps to go to much higher frequencies, let's say. And then other techniques like O-bar have been proposed, where you have like 3 stacks, so plus minus polarization, alternated to like periodical thickness old polarization, which is done by 3 times bonding a film and polishing, or just transferring 3 times. But this technique, which allowed to go to much higher frequencies and to overcome the problem of impedance matching, too small resonators, and so on. So it's very nice technology, let's say. But the problem is that you need 3 times equivalent thickness. And already the devices, both devices based on lithium niobate, they are too expensive. The price is quite high for industry. So to repeat 3 times the same, it becomes too expensive for the publication. And also you need to obtain 3 films with equivalent thickness, with the same thickness. And by doing polishing, ion slicing is very difficult to get exactly the same thickness 3 times. So there is these limitations. And then, of course, if you use a membrane structures and so on, there is the power handling problems. And also, if you just use like simple bow device, ion slicing is limited to like 250 nanometers. If you want thinner, it becomes too complicated. So it also limits the frequency, but it's not the only limitation. There are several limitations on that. So if you look, well, it's old slide. I mean, I put this here like to show in 2014 already people have been trying to do by polishing, polishing the filters, when at that time they really badly controlled the thicknesses. That's why you made a lot of ripples here because of a bad control of the thickness. Now it was done much better. And so basically with single crystalline films with it was, I think, 300 nanometer thick film or 250, I don't remember, in this case, which come from COLT. Basically, we attained 7.6 gigahertz with electromechanical coupling of 18.5. But integration remains, so it was F-bar, so it's a membrane and piezoelectric film between electrodes. So integration is still complicated. The thickness control, okay, you can show a device and so on, but to control precisely, because device frequency is defined by thickness, so you need to control very precisely, and becomes complicated. And then, of course, there is the price question, the size of the resonator, and so on. And before our group work on the grown films, so it was work from Kadota, from Murata, who showed in 2010 that it's possible to grow C-axis oriented films on electrode. And we attained the frequency of 2.9 gigahertz with a coupling of 5.8%. But this C-axis orientation, it has the same or even slightly lower electromechanical coupling than aluminum nitride. It was not possible to compete at that time with aluminum nitride. We just simply do a sputtering. And then what we proposed is to grow 33Y-oriented lithium niobate or 012-oriented lithium niobate, which offers material coupling of 24.3% for longitudinal wave. And also it offers a pure longitudinal wave. So if we look here, it's the maximum which is possible for lithium niobate for longitudinal wave. So we first, in very early work, we tried to grow this orientation on the silicon directly, on silicon, and then molecular beam and strontium titanate buffer layer, which is grown by MBE. So it's known template, which was used for barium titanate, PZT, and so on in perovskite community. So it nicely grows this with that orientation on a strontium titanate. Of course, initially we had to optimize the compositions because strontium titanate is not necessarily stoichiometric and lithium niobate as well when you grow. So if we had an excess of lithium oxide, we had the parasitic orientations. If we have strontium excess as well, we had the problems with interdiffusion and so on. So it really, both materials had to be stoichiometric. I mean, you don't have much problems if you grow on strontium titanate single crystals, but when you grow on strontium titanate thin film, because it's non-stoichiometric, when you get very easily interdiffusions and parasitical phases due to interaction between two films. And we had also some competition between 113 orientation and 012 orientation growth. So basically, we needed to play on the temperature to favor this orientation of 012. And 113 orientation is not really interesting. It corresponds to X30 degrees, but the coupling is like at least twice lower than that of 012 orientation. So we optimized this, and then we checked we had very similar quality if we would grow lithium niobate directly on the strontium titanate. So the rocking curves were relatively large, but because the films has a tilt from the substrate, we have about, basically the film in that case is not Y33, it's Y36, because the film is tilted from a substrate plane by 3 degrees. But when to go further, we needed to grow electrode, Bragg mirror epitaxially, sacrificial layers, and so on. It was quite a lot of work. And well, we grew platinum 100 epitaxial on this template, but it was complicated to make all the complete structure for like BO devices. Now, we show that it's possible to do a layer transfer. So it would be possible to use this template and to do a big scale lithium niobate 012 orientation or Y36 orientation transfer on the big substrates. We show also that the film, of course, as it's grown and the substrate is non-ferroelectric, we had the ferroelectric domains, plus and minus, okay? And we had 4 orientations in the plane because strontium titanate is a cubic, and this orientation of lithium niobate is pseudo-cubic. So it's not 4 axis equivalent, you have just one single polarization axis. So here you see this is the C-axis pole figure, so we have 4 orientations in the plane. So then at the end we found another like seed layer, which would allow us to grow on any substrate, this orientation, and it was lanthanum nickelate. So lanthanum nickelate is also a very known material in perovskite community, and is used as the seed layer for PZT and so on. So we can sputter 012 orientation. I'm sorry, I'm speaking in hexagonal unit cell. For people who use pseudo-cubic, it would be 100 orientation. Because it's trigonal material as lithium niobate, and lithium niobate, I always use hexagonal unit cell. So we can grow with 012 of lanthanum nickelate just by sputtering, and we can sputter on any substrate, just goes naturally by this orientation. So as you see here, this is a silicon with a platinum electrode, which is 111. So it's a sputtered platinum standard electrode, and then we grew this buffer seed layer of lanthanum nickelate, and then which allowed us to grow lithium niobate of 012 orientation on the top. So it grows very nicely on that. And then finally, we had to abandon silicon because all the films have been cracked on silicon, because the thermal expansion of lithium niobate now is like 10 times almost higher than silicon. So it develops it cracks very easily, even if a film is quite thin, like 100 nanometers. So we replaced silicon by sapphire just to reduce the thermal stresses. But basically, it can be also the substrate of lithium niobate and so on. It can be any other substrate which don't have such big difference. It can be quartz, which don't have such big thermal expansion difference. But again, we use the platinum, which is sputtered, which is 111, and again, sputtering of lanthanum nickelate, and then we grew lithium niobate. So we had very nice rocking curve, and we had some preference orientation. I don't put, but because basically, even if you grew very fast platinum and sapphire, it was like in 2 minutes, we grew 100 nanometers. Platinum is epitaxial. It's 111, but it's epitaxial. And it made that lanthanum nickelate normally is not oriented in the plane as well, so it's like sort of textured, but it has these two preferred orientations. As we see here in this pole figure, we see that there is some preference in lithium niobate in these two orientations. So it's textured film, it means like fiber texture, okay? There is no in plane orientation, but there is some preference in two orientations. When we measure the Raman spectra on these films, so when here we get to the case when the films are textured, so it means we don't have in plane orientation, and Raman spectroscopy is very sensitive to that because we have, if we don't, and the films have tilted orientation of a polar axis of a z-axis, which is at 57 degrees. So basically, we have oblique mode presence, which makes that when I do in a single crystal, I can properly separate like parallel and cross polarizations. But when I do thin film, I cannot do polarization separation. I cannot separate properly these modes because the film don't have in plane orientation. So basically, I have also the oblique mode presence. And then I have to analyze the broadening of the modes with respect to the defects. It becomes very complicated. But anyway, if I look and compare to the single crystal mode, probably my film contains more of lithium than the single crystal, than the congruent composition. So here we see the ferroelectric hysteresis measured for films. So we had slightly smaller quartz field as a congruent single crystal film, but this is because probably we have more of lithium. Again, polarization was slightly higher than expected. Then some of the films have been self-poled, some have been like polydomain. So I have here an example which was done in Jirka Klinka group in a seminar. And here we had an example where the films have been poled, self-poled. Okay, so we don't have plus and minus polarization, but some of them have been not self-poled. And then, for example, if you measure paraelectric current, we see that the paraelectric current is reduced. And after the polling cycle, it's increased more or less paraelectric coefficient to that what we expect for the single crystal films. Then another thing which is nice, let's say nice, in textured films, or this Y33 orientation. If you look here, we have this in red and blue E31 coefficient as a function of angle in the plane. Okay, so we see this is very anisotropic, but if you look to this Y33 orientation, which is here, sorry, it's not in plane angle. It is, or it's rotation around x-axis. So it means you start from z-axis, then you get to at 90 degrees to minus y, 180 it will be minus z, and 270 it will be y-axis. Okay, so when we get to Y33 orientations, let's say here, we see that E31 and E32 were isotropic. So when we see to the rotated tensor, we see that E31 and E32 were almost equal. So it means nice when you have a textured film, you will not lose this coefficient because you will make a homogenization of this coefficient. But another way, when you have this textured film, so likely we would add additional symmetry, some coefficients will go close to zero. So for example, if we take E34 coefficient, it becomes zero in textured, and this coefficient makes that we have a shear wave in a single crystal films. In a textured film, shear waves will not be never excited because this coefficient is zero in this Y33 orientation. So here I put you the shear coefficients well, we have longitudinal coupling, what I have been talking in blue, and S is for shear waves. So 3,5 is always zero, even for single crystal. But 3,4, so for example, if you take Y33 orientation, you will still have a little bit of coupling for the shear wave. So basically, the preference would be to 36, a few degrees off, where the shear wave starts to be zero. Okay, like this, you do not excite the shear wave and you get pure longitudinal. But in the textured film, this coefficient is zero. So basically, you never excite this shear wave in Y33 oriented films. So we measured this E31 coefficient. We measured E31 coefficient, and basically it was the same as very close to that measured with the same technique on Y36 oriented lithium niobate, say single crystal films. And we measured the electric constant. Of course, you need to be very precise on the thickness to tell exactly, but it seems to be a little bit lower, the electric constant, than that of a bulk. But the tangent loss is the same. So it's in 10⁻³ order. So it means very low tangent loss. Then we did also some F-bars. I didn't put the right image to change, but I had no time to do it before we started the seminar due to some delays today. So we did F-bars at different frequencies. So here I show you an example where it's not exactly the same coupling. We see that the film has lower coupling, but on the same wafer. Finally, I found also the coupling exactly as expected theoretically. So it really depends. In some places, the films are self-powered. And this is, well, nice, but still we need to be reproducible and to do a polling everywhere to get everything repeated. But we were able to get to quite high frequencies, like 4.5 gigahertz, 5 gigahertz, and so on, depending on the thickness of the film. If you went a little bit smaller, well, the best was when we connected. Well, we always have a problem if you look here with impedance matching. I mean, we are not at 50 ohms. We should be at 50 ohms. And so what I didn't add to the presentation today, we have the results on the 5 resonators on series, which we attain 50 ohms. But it was for the thinner film. It was 200 nanometers. So we have like 5 resonators in series, and then we get 50 ohms, and the coupling was nice for these films. So if we go to 130 nanometer thick films, so the size of device is already 1000 microns, so impedance matching is very bad, and then signal, of course, it's very bad because we are badly matched to our circuit. So the frequencies, let's say the film is very thin, but it remains low, but because it's F-bar, so the structure is very heavy for a film to move, and the frequency is really damped. We also use platinum electrodes, which is very heavy, so it doesn't really, we need to make a real TF bar and so on to show the real performance of a film in terms of, but in our lab, we are not very good at making membranes, so we decided to do SMRs and mirrors in collaboration with Marta's group in Madrid. And so we tried several types of mirrors, and well, in that center, we tried to grow zinc oxide platinum. Well, it's not a very good mirror, maybe from the price point of view. And then we had a problem with zinc oxide chemical instability, because when we did other steps for electrodes and so on, some parts etched out and we peeled out all the layers. So then we moved to the Marta's mirrors on silicon dioxide and tantalum oxide. So we targeted for the film 230 nanometer thick lithium niobate film. During, I had not so much mirrors, and I missed some steps for bottom electrode preparation and so on. And then I did my lithium niobate growth, the clean room during the night stopped, the cooling water, and my machine stopped at 175 nanometers. So we missed the thickness, the targeted thickness. So probably our mirror is not, and mirror was also annealed because the mirror was done at room temperature. The thickness should be moved out from these, let's say, absolute values what we expected. So probably the mirror was not perfectly reflecting the wave. And then we see these small ripples on the side. So this is that the mirror probably is not working perfectly, but we had a nice resonance at 7 gigahertz. Yeah, and then we used just a floating electrode and we measured coupling about 6%, more or less. Let's say the signal is a little bit maybe noisy. And then if we compare if it's good or bad, so the only reference which I have is also again from Katoda group. So we did very similar mirror, not tantalum oxide, but tantalum silicon dioxide with 500 nanometers lithium niobate Y36 cut. So it's a single crystalline polished film with aluminum titanium electrodes. And we were almost exactly at the same frequency as me, but we had 8% coupling. We also had some problems with the fabrication, if I remember well, on the mirror or something like this. We had also a problem with fabrication on this device. And you see my film is much thinner, so already I would expect much lower coupling, and my electrode is very heavy, platinum, so it means the coupling is killed as well. So the coupling is not that bad of the film if we compare it. It's relatively, let's say, comparable. But we need to redo everything, let's say, more properly to show the real performance of these films. And now basically what we are trying, we are moving over group, we are moving to the layer transfer. So basically, because we see that if you want really to make a competition with the single crystal films, so ion sliced films, everyone's single crystalline films on any substrate, on any structure, and so on. So that's why we're starting more and more to work on layer transfer technique for lithium niobate when we use a lithium as a substrate. And then we do a sacrificial layer, and then we grow lithium niobate on the top. So today we have found a nice sacrificial layer, which I cannot tell you what is it because we are patenting at the moment, but which allows us to keep the ferroelectric domain structure. So it means that the films follows the single ferroelectric domain structure from the substrate, and we have very nice, let's say, rocking curves, much better than on Sapphire. And here you see, well, this is a phi scan comparison. Okay, so if I grow on Sapphire, this is for X-cut lithium niobate, which is interesting for photonics. So we grew the films without cracks and any problems with 680 nanometer thickness. And we see that we don't have two orientations in the plane. When we grow on Sapphire, we have X plus and X minus growing together. On lithium niobate substrates, which have just single orientation. If substrate is X plus, it grows X plus. If it's X minus, it will be X minus. And the rocking curve, we see it's very, very close. The substrate, so it's the resolution of the diffractometer, and the rocking curve is 0.092. Yeah, so basically we can grow any orientation, and the thickness, well, it depends probably on time and so on. The roughness is still important, like 6 nanometers, so probably we can do a polishing. And we have some layer transfer results on silicon dioxide, but it was some problems with silicon dioxide quality because we had etching by Piranha was starting to etch silicon dioxide, but it was the first results where we transferred all the process bonding and so on is done on 4-inch wafers, but when we dice, because we cannot etch all the lithium niobate substrate, so we dice to the smaller pieces to liberate faster. So this is like where you see it's a diced pieces. So basically where we move now, our group, is to this lithium niobate and lithium niobate single crystalline quality films, and then a layer transfer to the different type of devices. And then to finish, it's an old photo of my previous PhD students. I have to make a new one to thank the new students. But these students contributed a lot to all the results which I'm showing here and what I showed today. So thank you very much for your attention, and it's a time for probably questions if you have some.
Thanks for a nice talk. I have 2 questions.
Okay.
So can you comment, is there any effort on lithium tantalate in terms of thin film?
Yeah, well, in our, I mean, if we look on ion slicing and polishing, we are both people work on both on lithium tantalate and lithium niobate.
Yeah.
Then in our group on the growth, we have demands and we will start to work this summer. But so far, the demands were much bigger on lithium niobate. I did many years ago some growth of lithium tantalate, but all the projects have been always on lithium niobate.
Yeah.
So
they're actually very similar.
It's always I have one machine for growing lithium niobate, so it's always a question of trade-off. What is the demand? What is the project on? But I have a new demand on lithium tantalate, and it will come lithium tantalate. So this summer probably we will start on lithium tantalate as well.
I just wonder whether in terms of thermal expansion coefficient, whether it would be...
No, a thermal expansion is the same problem.
Same problem, okay.
Exactly the same problem. So it would not really help from this point if you want to grow on sapphire. But then for layer transfer, we can still consider the same strategies. It's very close from the structure.
Right. So, yeah. And then my second question is concerning the Raman spectroscopy. So essentially from the broadening, you determine the composition?
Yes.
And then do you have like a standard calibration?
So basically I have well, you can find of some thesis of mine, but it was very known in literature, but I never use a calibration from literature. I always do my own calibration on my own machine. So I have a congruent crystals, and then I have also single stoichiometric crystals.
And then do you fit the oblique line shape?
Well, in these textured films, I did not estimate it. Like, it would be difficult to make absolute. Okay. So I don't really estimate. I just compare in relative scale.
And then how do you separate the strain effect? And
this is my paper in 2012.
2012. Okay, which journal?
Applied physics letters. I detailed quite a lot how to do it. So basically, you take different modes which has different sensitivity to the effect. But for example, you have some modes which shifts a lot, like E60 mode, which at 380, which shifts a lot with the stress. So basically, you take wave numbers, which is a little sensitive to the composition, and you estimate the stress. But you can also use X-ray diffraction. So I coupled like both. You can use X-ray diffraction because in X-ray diffraction, very frequently your composition shift is almost invisible. It depends on the resolution of your diffractometer, but it's very little with respect to the stress effect. So basically, you estimate stress effect from X-ray diffraction, and then there is some calibrations, which I give in the paper. Then you know how they change. But again, in the group, we did all these calibrations as a function of stoichiometry, as a function of stress, and so on. And then one German group, we published recently all the calibrations on the stress, so it can be taken from literature. And then when you know both effects, how the broadenings, how the shifts react to the different effects, then you can separate, because some modes are very sensitive to one effect and others to another one. So you can separate this.
Yeah, and then so what you showed in the slides was essentially just the broadening, but sometimes they also shift, or you also see shifts.
It's always both.
Okay, but
So
because from the slides, it looks more just like broadening.
Because the broadening is much more important when we shift.
Okay.
For the stoichiometry. So it depends on the mode, of course, but I mean, if you look to this E1TO, it's not the biggest broadening on this mode. I just use it because it's well separated from others for the fitting. But it's like you change from, if it's stoichiometric, it will be around 5 or 6. It depends on your spectrometer, but about, let's say, 5 reciprocal centimeters the width. And if you go to the congruent, you get to 10.
Okay.
So it's twice. So you get nice precision. And you can fit very well with mode because it's well isolated from others. So you can have very nice.
And then let's say you grow 2 films, so in 2 runs, exactly the same conditions. Will you see a different strain, or is more or less the same?
I don't think this, well, I never really compared like in details.
Okay.
This thing, but I think the strain, I mean, when the strain is high, it's very frequently about, if you go on Sapphire, on the C-axis, you will get to 1 gigapascal something.
Okay.
And you will see it each time more or less the same. But I never really compared. It has to be exactly the same thickness, the same cooling stuff, and so on. But normally it should be reproducible, I think. But I never did such like statistical, calculations. But from the different like periods, let's say, when we republished on a new campaign and so on, we always find more or less the same stress on these 100 something thick films. It was 1 gigapascal something always.
Thank you very much.
You're welcome. Some other question, because I don't see like.
May I just ask you, Jens speaking?
Yeah.
May I just ask about the layer transfer? Can you say a word how you do this? Do you do more like a wafer bonding process?
Yes. So we have like 2 processes targeted. One is the wafer bonding, so silicon dioxide wafer bonding. We did at some point also gold bonding, but now we have more like demands for photonics. So we do silicon dioxide bonding, and then you do like wet etching to liberate the layer. But as we do on a wafer scale, and I cannot etch over substrate, so I have to pre-dice my substrate to liberate the film. Yeah, and then the second project, which is that just started, so we still not have results, let's say, or didn't. So the student just will start to do it. It's a micro transfer. So basically the same structures, but when you just transfer a small piece, not all the wafer, which probably will be better adapted than this complete wafer bonding, which requires like dicing after a little bit, or to make some channels how the acid should attain your sacrificial layer.
Yes.
But if no, we do everything on 4-inch, but then at the end we cut.
And so for the microtransfer printing, you develop the templates, the transfer stamping templates
this
yourself,
part will be due in C2Zen, so it's not in my group. It's in Paris. Yeah, so we have a machine, and then we have like standard templates, so we will see what will give. But this part will be started to be done. So it will start with development. So it's still not done, but it is something what we plan to do.
Okay, thank you.
Okay. I even don't see how many people is online. I'll stop sharing. Okay, 28. We lost some of them. Okay. So I don't know if you have some question, just please lift. You don't need to lift the hand, just ask and.
Hello, can you hear me?
Yes. Yes.
Yeah, sorry. I didn't find actually the way to raise my hand during
No,
this
it's okay.
call.
Don't just ask. I say just ask. Don't raise your hand. Just ask.
Yeah, sure. So I wanted to ask actually, what is the like a more application interest of like depositing thin films of lithium niobate on sapphire?
Well, sapphire, I don't know if it's really have application today, real industrial application. In all the times when everybody thought about monolithic integration, it means we grow all the complete structure. We do all the complete structure without any layer transfer, any layer bonding, and so on. Sapphire was interesting to accelerate the waves, for example. But we do also a bonding on sapphire wafers because sapphire, it's a hard substrate. It has high acoustic velocity. So we can accelerate the waves and attain higher frequency. And then in photonics, it also has lower refraction index, so it can guide wave. But still, I don't think it's really competitive with silicon platform. But it was in all times. All we used. Everybody did on sapphire. It was like, now it's like a reference. You grow on sapphire. I mean, you check everything. When you work on lithium niobate, you need some reference on the side because it's not that easy to characterize lithium niobate on lithium niobate.
All right. Yeah, thank you so much. And secondly, I wanted to ask what was the pure electricity, right? Those slides that you have shown. Could you elaborate a little bit on that part as well, please?
You mean what was the coefficient? It was 60 microcoulomb. It was like more or less it's 1 microcoulomb per square meter per Kelvin. This was more or less what was expected for lithium niobate for that orientation. So yeah, you put electrodes and then you heat up, you cycle the temperature and you measure your coefficient.
Oh, all right. Yeah. Okay. Yeah. Thank you so much.
It's more like secondary effect in lithium niobate. In lithium tantalate, it's used in sensors. In lithium niobate, it's less used. It could be used for some sensors, but it's not. Lithium tantalate has much higher pyroelectric effect, so it's used in lithium tantalate.
Oh, okay. I see. Yep. Thank you so much.
You're welcome.
Ausrine, may I ask a question?
Yes, sure.
This is Shuji Tanaka. Thank you for inviting us to this great seminar. So if we use the layer transfer technology, we doesn't care the substrate. So maybe we can use the lithium niobate as a starting substrate. It may relax the CT mismatch problem. So you didn't mention about the homoepitaxial growth in this seminar. Is there any advantage to you?
It is almost homoepitaxial, what I showed in the last slide, lithium niobate on lithium niobate.
Oh, I see. No, it's not on the sapphire.
No. The last, wait, I'll share
Okay.
Again my screen. This is, wait, I didn't click probably. Just give me a small minute while I partage it. Okay, so if I go to my last slide here, this slide.
Okay.
So it is lithium niobate on lithium niobate. Okay.
Okay, good.
We have sacrificial layer, which is very close to lithium niobate. So it's basically almost homoepitaxial conditions. And then we have this, as the composition is not the same here, I know you can see. So I'm able to see it in X-ray diffraction to separate the rocking curves in the high resolution diffractometer. Okay, but we have a single orientation in the plane. We don't have X plus, X minus. We don't have ferroelectric domains.
Okay, so in terms of film quality, is there any advantage in the homoepitaxial growth compared to the epitaxial on the sapphire or silicon?
Of course. If you look, for example, now this film is already very thick. You see, it's 680 millimeters, and you don't have any growth domains.
Oh.
It has very low rocking curve. Then the same film on sapphire, you see, this is for these phi scans, is much broader.
I see.
And then the film on sapphire with this thickness, it's already cracked. You have a domain, you have a twins, and you have a cracks, because
I
it
see.
relaxed it relaxed the stresses. Like this film, we don't have all these problems.
Okay. Thank you very much.
You're welcome.